Today in this video we will discuss non-isolated systems while dealing with momentum still. So now you have a system, let's say two particles, whatever forces they exert on each other. This is my system, but now this is non-isolated. Now there is some force is acting. There is some external force, or maybe there are a lot of forces, I don't know. Right, there's another external force 1, external force 2, external force 3. So now the system is non-isolated, right? So again, what Newton said is that the total force external is the change of momentum with respect to time. So if you want to know how the momentum is changing, well, now it's not going to be zero because now there is, in fact, an external force or a net external force, right? And then what you will need to do is do the integral, but I'm just going to give you a definition first. The change in momentum will be equal to the net force average, right, times the time. And and then that's it, right? This will be momentum final minus momentum initial will be equal to the sum of the average force, which is a vector, I'm sorry I didn't put that, times time final minus time initial. Okay, this quantity here, force times time, it's called the impulse, right? Net force average times distance, remember, or displacement. Actually, you remember how this was the work back in chapter something 6? Well, now if you multiply the force times the displacement, you get work. If you multiply the force times the time, you get impulse. And impulse is a vector. So this is scalar, and this is a vector. So at the end, what I want to show you is that the change in momentum, which is a vector, is equal to the impulse. Right? And this is a very important equation as well. Is as important as the change in kinetic energy is equal to the work. Right? This is called the work kinetic energy theorem. This is called the impulse change of momentum theorem. And let me show you very quickly what's the difference between them. If I send a baseball with velocity v and mass m towards the catcher, right? So here's the glove. Oh my God, I'm so bad at drawing. So I don't know how to do this. Let's say this is the hand of the catcher, okay? That's a hand. So it's gonna catch the ball. Of course, this thing has an initial velocity. Hopefully, after it has catched the ball, the system is gonna look like this. So that's the hand, but now it got the ball was caught. Of course, here the final velocity is 0, right? The ball still has its same mass. If we were looking at this from the perspective of work, right, and the kinetic energy, we will have said, well, 1/2 of mv final square minus 1/2 of mv initial square, that's equal to the work, which is equal to the total force, which I'm going to write like this, times the displacement. So if you calculate the kinetic energy of the ball, you will be able to find, if you know the force of the catcher, you will be able to find over what distance the ball was stopped. But if you do this from the point of view of the impulse change of momentum, then this will be mass velocity final minus mass velocity initial is the same force as before. This is the same force, but now times the time. And what this equation will tell you is using the same force over what time interval, right? Well, here to here to here, what time interval was required for the ball to stop? So two different theorems. They both utilize mass and speed and force, but one tells you, one relates all this through this to displacement, the other one, this dot product, relates to the time interval. Let's consider this example. We have a crash test. We have the mass of the car. First is going at 15 meters per second towards the left, but then after colliding with the barrier, it moves actually to the right at 2.6 meters per second. The collision lasts 0.15 seconds, so find the impulse. Okay, so the equation is that because of the external force, the impulse is the change in momentum, which is going to be mass velocity final. I'm going to do all in x, okay? All in x, so I don't have to write x everywhere. So mass times velocity final minus mass times velocity initial, right? We also know that this is going to be equal to the total force, the total external force times the time. That's because they want us to find the impulse and the net force. So just by finding the impulse from the right side, the left side of this equation, all we have to do is mass, 1500 kilogram, and I'm just going to factor the mass. So speed final is plus 2.6 I, and then minus, and the initial velocity is minus 15 I. Right, so then we multiply this. There you go, and the impulse is going to be 2.64 times 10 to the 4 kilogram meter per second, which are kilograms times meters per second. This was meters per second, the speed in the I direction. So that's a vector, that's the impulse. So what is if that's equal to force external, net force times time, then the net force exerted by the wall here is the impulse over the time. So 2.64 to the 4, all of those units, kilogram meter seconds, and the time was 0.15. So this gives us 1.76 to the 5 newtons, also in the I direction. So the system, of course, was the car, and then the wall was what provided the external force. Okay. You could do this also as an isolated system, but that would not give you the force because this internal disappears from the equation. So instead, we used the non-isolated to see what that external force was going to look like. There you go, impulse and change of momentum in non-isolated systems.